Welcome viewers. Today's topic is diagonalization of square matrices. To start this topic, I will first like to review what we have done in eigenvalue problem. By eigenvalue problem, we mean that for a given linear operator, find those vectors which transform to their scalar multiples under the transformation Ax is equal to lambda x, where A is a square matrix associated with the linear operator, x is called an eigenvector and lambda is the associated eigenvalue. By this I mean that if a vector x is given, that under this transformation it will become Ax in such a way that the the transformed vector Ax is parallel to x, but its scale has changed. If the scaling factor lambda is bigger than 1, then it is magnified, and if scaling factor is lambda is less than 1, then x will be contracted, and when lambda is negative, the direction will be changed. We have performed various manipulations on eigenvalue problem, and we have seen that the algebra on diagonal matrices is much simpler. So, and similar matrices share many properties. This has also been established in one of my earlier lectures. Start. Given a square matrix, does there exist a non-singular matrix P such that P inverse AP is a diagonal matrix? By this I mean to say that if I have a square matrix A, can I find a matrix P so that it is similar to a diagonal matrix, and the matrix is obtained as P inverse AP. We have seen that P inverse AP is similar to A, and this will be a diagonal matrix, and that we can easily perform variety of algebraic operations on the diagonal matrices. So, if we can perform operations on the diagonal matrices, we can perform operations on the square matrix A. So, that is the purpose of diagonalization of a square matrix. So, we want to find out under what conditions the matrix A can be diagonalized, that is, under what condition it is possible to find P, and if it is possible to find P, then what is P? So, first we have to establish the existence of P, and then we have to find P. So, that these are the issues which are related with diagonalization problem. So, I will first give the definition. A matrix A is diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix, and in such a case we say that the matrix P is said to diagonalize A. A matrix A is diagonalizable if it is similar to a diagonal matrix. We have already seen that if there exists a matrix like P inverse AP, then A and P inverse AP, they are similar. So, a matrix A is diagonalizable simply means that it is similar to a diagonal matrix. Now, for this, this theorem will be helpful. So, let me first state the theorem. For a square matrix A, the following are equivalent. A is that A is diagonalizable, and B is that it has n linearly independent eigenvectors. Now, to prove this theorem, I will first prove that if A is diagonalizable, then it has n linearly independent eigenvectors, but since this theorem suggests that these two statements are equivalent, so I have also to prove that it has n linearly independent eigenvector means that A is diagonalizable. So, first I will prove the forward part, that is, suppose A is diagonalizable, then there exists a non-singular matrix P such that P inverse AP is equal to D. Now, P has to be invertible because we need P inverse. So, A has to be diagonalizable means P inverse AP is equal to a diagonal matrix D, and we can write down this equation in an alternative form. AP is equal to PD, and this can be obtained by pre-multiplying equation 1 by P. Now, let us calculate AP. So, if A is this matrix, n by n matrix, and P is this square matrix, then let us try to find out the product matrix. Now, I write down this product matrix as this row vector in which AP1 is the product of A matrix with the column P1. So, this I call as P1. So, first element in this row is AP1, this matrix multiplied by this column. The second element will be this matrix multiplied by this column, and this is the jth entry in this product, and APN is the last entry. Then APJ is the jth column of the product matrix AP, where APJ is this I have already explained. Now, considering the right hand side, PD is equal to the matrix P multiplied by the diagonal matrix. Now, this matrix P is already been explained, and this diagonal matrix will have eigenvalues in the diagonal. So, the matrix is diagonalizable means that we have matrix A is equal to P inverse PD, where D is a diagonal matrix consisting of eigenvalues. So, if we have eigenvalues lambda 1, lambda 2, lambda n for the given matrix A, then D will be given by this diagonal matrix. And then I can perform the multiplication. It is P11 and lambda 1 first element, then we will have P12 lambda 2, this is the second element, and then we will have lambda n P1 n, this will be obtained when this is multiplied by this column. Similarly, P21 multiplied by this is this element, and P2 this row multiplied by the second column will be this element, and so on. So, this is the product of these two matrices. Then we can rewrite this matrix as a row matrix, where we will have lambda 1 P1 is the first element, lambda 2 P2 is the second element, and so on. What is P1? P1 is actually a column vector, this. So, P1 is nothing but first column vector, P2 is nothing but the second column vector, and Pn is the nth column vector of this matrix. So, we have simplified PD in this form. And now, if we compare what we had for the earlier expression, then we say that APJ, which we have computed in the last slide, is equal to lambda j Pj. So, this is lambda j Pj, and what we have obtained earlier is APJ. Then we can say that Pj is the eigenvector corresponding to eigenvalue lambda j of the matrix A, and the matrix P consists of columns of eigenvectors of A, that is what we have seen. And since P is invertible, all the eigenvectors are linearly independent. This is the result which we have established earlier. So, the matrix A has n linearly independent eigenvectors, and if they are linearly independent, then we have proved the result. So, if we have a diagonalizable, if A is diagonalizable, then it will have n linearly independent vectors. Now, if it has the inverse part is that if it has n linearly independent vectors, then it is diagonalizable. So, let us prove the reverse part of the theorem. So, we have let A has n linearly independent eigenvectors, then this means if lambda 1, lambda 2, lambda n are n eigenvectors of eigenvalues of A, then x1, x2, xn are linearly independent. That has been given to us. And let P be the matrix whose columns are eigenvectors of A. So, this is the matrix. Let us form the matrix P with eigenvectors, and they are linearly independent. So, this is the first column P1, then the second column P2, and so on. Now, AP will be AP1, AP2, APJ, APN, this we have already explained. And now, AP1 is equal to lambda 1 P1, AP2 is equal to lambda 2 P2, and so on. So, we can say that APJ is equal to lambda JPJ, and from here we can say lambda 1 P1, lambda 2 P2, lambda j Pj and lambda j Pn is equal to this matrix. This we have already seen. So, it is nothing but P11, P21, Pnj the first column, P12, P22, P2 in the second column, and this is multiplied by this matrix. So, actually we are retracing the steps what we have done in the forward part. So, this product is equal to PD. So, we have AP is equal to PD, and from here, since P is invertible, we can write down D is equal to P inverse AP. So, we have started with n independent eigenvectors, and we could prove that the matrix A is similar to D, and that proves that A is diagonalizable. Now, the diagonal elements of D are the eigenvalues of A, this we have already observed, and the columns of matrix P are eigenvectors of A. So, we know how to form the matrix P, and this matrix P is invertible because it forms the n columns of n independent vectors. So, this forms a basis for finding diagonalizing a given matrix. So, let us discuss the procedure for diagonalization. So, the first step is that you have to find n independent eigenvectors for a given matrix A. Then in the second step, we form the matrix P with columns as independent eigenvectors. Then third step is calculate P inverse, and fourth step is form the product P inverse AP, and this will be the diagonal matrix D. So, we apply this procedure to diagonalize the matrices, the square matrices. So, I will start with this example. First, we consider a 3 by 3 matrix 4 minus 1 5 0 6 0 1 minus 2 and 0. So, let us consider this square matrix. One can find out that the eigenvalues of this matrix is minus 1, 5 and 6. Actually, this problem was solved earlier, where we have obtained eigenvalues of this matrix and we have obtained the eigenvectors of this matrix. Either you go through the lecture or you can take it as an exercise to compute the eigenvalues and corresponding eigenvectors. For this example, minus 1, 5 and 6 are the eigenvalues, and the corresponding eigenvectors are minus 1, 0, 1 for lambda is equal to minus 1. For lambda is equal to 5, eigenvectors are computed as 5, 0, 1, and for 6, eigenvectors are computed as 16, minus 7 and 5. With these eigenvectors, which are linearly independent, one can form the matrix P. So, this is the first eigenvector, forms the first column, the second eigenvector forms the second column, third eigenvector forms the third column. So, that is my matrix. Now, since this matrix is invertible, consisting of linearly independent eigenvectors, so we have to find out its inverse, and its inverse is adjoint P divided by determinant P. So, let me first calculate determinant P, and this comes out to be this determinant, which is computed as minus 42, and we calculate the adjoint P as this matrix of subdeterminants. We take the transpose, and this can be easily verified that this is adjoint of P, and once we get this adjoint, we can write down P inverse as this matrix. So, once we have P inverse, we can calculate P inverse A. So, this is my P inverse and this is the given matrix A. Perform this multiplication and this comes out to be this matrix. One can check different terms here. After that, given this P inverse A, one can write down P inverse AP, that means multiply this matrix by the matrix P. So, this is the matrix P which I had obtained. So, this multiplied by this, when you perform this multiplication, this comes out to be this matrix, and one can notice that this -1, 5 and 6, these are the diagonal elements which are actually the eigenvalues of the given matrix A. One can check, if you first perform this row multiplied by this, we will get -1, and when this is multiplied by this, one can check that this comes out to be 0, and so on. So, P inverse AP is a diagonal matrix, and we say the matrix is diagonalized. But if we consider the second problem consisting of a 2 by 2 matrix, then we had already observed that lambda is equal to 4 is an eigenvalue of multiplicity 2. This I have done in one of my earlier lectures, or you can take it again as an exercise and check that lambda is equal to 4 is an eigenvalue of multiplicity 2. But we have seen that it has only one independent eigenvector, and this means that it is not diagonalizable. We cannot find a matrix P which is not which is invertible, so it is not diagonalizable. Now, this is another example, a 3 by 3 matrix. This matrix has eigenvalues -1, -1 and 7. One can take this an exercise to check. Then lambda is equal to 7 is the eigenvector corresponding to lambda is equal to 7 is -1, -2, 1. Again, this may be an exercise for you. For lambda is equal to -1, we consider the system A minus lambda I x is equal to 0, and this system is 1, 2, -3, 2, 4, -6, -1, -2, 3, that is the matrix A minus lambda I. We apply a linear transformation on this matrix, and we find that this row and this row, they are proportional. Not only this row and this row, they are also proportional. So, there is only one independent row, and the other two rows can be transformed to 0 rows by using appropriate elementary transformations. And this suggests that this matrix has only this suggests that this has nullity 2 and rank 1. That means we can find two independent eigenvectors corresponding to lambda is equal to -1. So, this problem is different than what we had in the earlier problem. In the earlier problem, we had a root of multiplicity 2, but we could find only one independent eigenvector. But in this case, the multiplicity is 2 and we can find two independent eigenvectors. Now, these two independent eigenvectors can be obtained as 3k minus 2r, r and k. How? We can assign x, y and z arbitrary values r and k, and then if we substitute this as y is equal to r and z is equal to k in this equation, then 3k minus 2r comma r comma k will satisfy this multiplied by x equal to 0. So, the eigenvalue corresponding to lambda is equal to -1 will be given by this, and now we can assign independent values to r and k. So, if I write down r is equal to 0, then eigenvalue will be 3, 0, 1, and when I independently assign 0 to the arbitrary constant k, then -2, 1, 0 will be an eigenvector. And since I can assign these two values independent of each other, so we can say that these two are independent eigenvectors. So, corresponding to lambda is equal to -1, we could obtain two independent eigenvectors. So, we had three eigenvalues, lambda is equal to 7, lambda is equal to -1 and lambda is equal to -1, and we could get three independent eigenvectors. So, the matrix P will now be 3, 0, 1 cos this, -2, 1, 0 corresponding to lambda is equal to -1, and the third one is -1, -2, 1. So, this matrix P is invertible. Now, we can obtain its determinant as 8, and this value can be used here to get the adjoint P, and from where we can get P inverse. So, adjoint P is calculated as this, and P inverse comes out to be 1 by 8 of this matrix. So, we have obtained P, we have obtained P inverse. Let us check whether they give rise to they give rise to a diagonal matrix. So, for this purpose we compute P inverse A. So, this is my P inverse which I have computed here, and this is given A. So, I compute P inverse A as the product of these two matrices, which can be computed here, and the details are given here, and finally P inverse A comes out to be this 3 by 3 matrix. After computing P inverse A, we can multiply it by P to get P inverse AP, and this calculation can be done here, and if you multiply this row by this column, we will get minus 8, but when you multiply this row by this, it is 0, this multiplied by this is again 0. So, this way you can you can calculate individual elements of this matrix, and this comes out to be this, and you can simplify it as minus 1, 7 in the diagonal, and this is a diagonal matrix. So, we have started with a matrix A, we have obtained the matrix P, then the next step we have obtained P inverse, and when we multiply these two, we find the diagonal matrix this, and mind here that minus 1 are the repeated roots of the given matrix, and 7 is the another eigenvalue of the matrix. So, this diagonal matrix constitute the eigenvalues of the given matrix A. So, in this example, although we have repeated roots, but still the matrix P can be obtained, it is invertible, and the matrix A can be diagonalized. So, we have 3 examples. In the first example, we have all distinct roots. In the second example, we have 2 repeated roots, but the matrix cannot be diagonalized, and in the third example, we have repeated roots, but still the matrix can be diagonalized. So, we can say that the eigenvectors V1, V2, Vn corresponding to distinct eigenvalues lambda 1, lambda 2, lambda n are linearly independent. This is the result which I have already discussed in my earlier lecture on eigenvalues and eigenvectors. So, this we have confirmed here also, and then matrix having n distinct eigenvalues is diagonalizable. So, if a matrix has distinct eigenvalues, then we can find distinct and independent, linearly independent eigenvectors, and the matrix can be diagonalized. But if the roots of the characteristic polynomial are real but not distinct, then we may be able to diagonalize it or we may not. Like in one example I have shown that it cannot be diagonalized, while in another example the matrix can be diagonalized. Now, we say that n by n matrix is not diagonalizable if all characteristic roots are not real. So, if we have complex roots, then of course, the matrix cannot be diagonalized, but if they are real and distinct, it can be diagonalized. And the second is, if it does not have n linearly independent eigenvectors, then again it is not diagonalizable. Now, the theorem which we have discussed, that is useful in diagonalizing the matrix. Now, we talk about diagonalization of symmetric matrices. Now, this is important because we have already seen that all the roots of characteristic equation of a symmetric matrix are real. So, this is one condition for diagonalization of a matrix. All the roots should be real, then if they are distinct, then it is diagonalizable. So, if all the roots of a characteristic equation of a symmetric matrix are real, so symmetric matrix can be diagonalized. Further, a symmetric matrix with distinct eigenvalues is diagonalizable. So, symmetric matrices is one category of matrices which can be diagonalized. Now, we give some definitions. If lambda is equal to lambda naught is an eigenvalue, then we say it is of algebraic multiplicity R if lambda minus lambda naught raised to power R is a factor in the characteristic equation. So, like in the examples which we have taken, the root is appearing twice, lambda plus 1 raised to power 2. So, we say multiplicity of the root is 2. Apart from this, we associate geometric multiplicity of the root, lambda is equal to lambda naught, and we say that P is the geometric multiplicity of the root if there are at most P independent eigenvectors corresponding to lambda naught. Like in the first example, multiplicity was 2, but geometric multiplicity comes out to be 1. But in the second example, algebraic multiplicity is 2, but also the geometric multiplicity is also 2, and in that case we have 2 independent eigenvectors, and that means the matrix can be diagonalized. Now, this is related with the dimension of eigenspace. So, we say that the geometric multiplicity is the same as dimension of the eigenspace. So, we can easily check that geometric multiplicity is always less than algebraic multiplicity. The number of independent roots will always be less than the multiplicity. It can at most be equal to the algebraic multiplicity, but cannot exceed this. And in the case if A is diagonalizable, if and only if for every eigenvalue geometric multiplicity is equal to the algebraic multiplicity. If this is true for each and every eigenvalue, only then A is diagonalizable. So, this is the condition on A which suggests whether a matrix is diagonalizable or not, because this condition ensures that existence of n independent eigenvectors even if the roots are repeated. So, we do not have to worry about whether we can get the independent vectors or not. We simply check what is the geometric multiplicity, and if geometric multiplicity of each root is the same as algebraic multiplicity, then existence of n independent eigenvectors are possible, and we can say the matrix can be diagonalized, because in that case the existence of non-singular matrix P is possible, and that leads to diagonalization of the matrix A. So, if we can find P, if we can find n independent vectors, we can find P, and once we can find P, the matrix is diagonalizable, but still there is a difficulty. Although theoretically P is invertible, so P inverse is possible, and once we can find P inverse, then P inverse AP will be diagonalized. But many times finding P inverse is not simple. Lot of computational effort is required in finding P inverse. For this purpose, we introduce another concept that is called orthogonally diagonalizable. So, we say a matrix is orthogonally diagonalizable if there exists an orthogonal matrix P such that D is equal to P inverse AP. Now, it is first thing is that the matrix A is diagonalizable. So, there has to have some P and P inverse, so that D becomes P inverse AP. But the matrix is orthogonally diagonalizable means there exists an orthogonal matrix which is satisfying this property that A inverse is equal to A transpose. And if A inverse is equal to A transpose, we can straight away write D is equal to P transpose AP. So, we do not have to find out P inverse in that case. Finding transpose is simple as compared to finding inverse. So, this is simpler than what we had earlier. So, this is the purpose of defining orthogonally diagonalizable matrices. So, we define a matrix is orthogonally diagonalizable if we can have a matrix P such that D is equal to P transpose AP. Now, there are many issues with orthogonally diagonalizable matrices. The issues are what are the matrices which can be orthogonally diagonalizable, and what are the characteristics of such matrices, and if they are orthogonally diagonalizable, then what is P, and once we can find P, then of course P transform is P transpose is simple and one can easily find out D. So, let us discuss this theorem, according to which a square matrix A, for a given square matrix A, the following are equivalent. The first is that A is orthogonally diagonalizable. The second statement is that A has orthonormal set of n vectors, and the third statement is that A is symmetric. So, these three statements are equivalent. By this I mean to say, if A is true, then B is also true, and if B is true, then A is also true. Also, B implies C and C implies B. Not only this, A implies C and C implies A. So, number of things have to be proved if this theorem is to be proved. We will do one by one. So, first step is that if A is orthogonally diagonalizable, then it will have an orthonormal set of n vectors. So, that is A implies B. So, given that A is orthogonally diagonalizable, we have to prove that it has a set of n orthonormal vectors. So, A has orthonormal set of vectors. So, since A is orthogonally diagonalizable, so there exists P such that P inverse is equal to PT, because this matrix P has to be orthogonal. So, P inverse is equal to PT and D is equal to P transpose AP. So, this product is a diagonal matrix, and since PT and P inverse are same, so D is equal to P inverse AP. So, D is similar to P inverse AP as well as it is similar to P transpose AP. So, that is been given to us. From here one can notice that a matrix A is orthogonally diagonalizable means that matrix A is diagonalizable, because we can find D, we can express P inverse AP as D, and that means the eigenvalues in P are linearly independent, because the matrix A is diagonalizable. So, its eigenvalues are linearly independent, and linearly independent vectors are orthogonal, we know. So, this implies this, and that means the matrix B, which is set of eigenvectors P multiplied by PT, P transpose is equal to I. The matrix is orthogonal. So, this statement means that Bij is equal to 0 whenever I is not equal to j, and it is 1 when I equal to j. This P matrix, if you look at this product, then Bij, the typical element in B, is obtained as the ith row of A is multiplied by jth column of A transpose. But what is ith row of A? Is the ith row of A multiplied by jth row of A. It is A transpose. So, this column is replaced by row. So, two rows of A are multiplied, and this is equal to 0 when I and j are distinct, because they are independent vectors. So, this is going to be 0 when I and j are distinct, and when I is equal to j, then this ith vector of A is multiplied by ith jth row of A or ith row of A, that means two vectors are multiplied, and this has to be equal to 1 according to this, because our claim is that D is an orthonormal matrix. So, for I is equal to j, this product is equal to 1, and that means the column vectors of P are orthonormal, because their product is equal to 1 when I is equal to I and when they are different, then it is 1, and this means that column vectors of P are orthonormal. So, we can say that A has orthonormal eigenvector. So, this was to be proved. So, we have started with orthogonal diagonalization of A, and we have proved that the matrix A has orthonormal eigenvectors. So, if the matrix is orthogonally diagonalizable, then it will have orthonormal eigenvectors. So, this is the first part of the theorem. The second part is that B implies A, that is, if P1, P2, Pn are orthonormal eigenvectors of A, that means the matrix A is orthogonally diagonalizable. So, for this, let us consider P as set of column vectors P1, P2, Pn, and these are orthonormal eigenvectors of the matrix A, and that means Pi Pj, its inner product is equal to 0 when I is not equal to j, and it is 1 when I is equal to j. In fact, when we are multiplying ith row with jth row, that is nothing but the inner product. Now, if we consider the product P transpose P, then rows of P transpose are multiplied by columns of P. So, each term will be of this form, and that means the term will either be 0 or 1. If it is 0, if I is not equal to j, it is 0, or it will be 1 when I is equal to j. That means P transpose P will be a matrix with 1 in the diagonal and rest of the elements are 0. That matrix is nothing but an identity matrix. So, P transpose P is equal to identity matrix. Similarly, one can prove that P transpose is also identity matrix, and once P satisfies this property, then one can say that P is a orthogonal matrix, and this proves that A is orthogonally diagonalizable. Then the next part of the theorem is that A implies C. That means, given D is equal to P transpose AP for a given matrix A, it is orthogonally diagonalizable, means there exists P matrix such that P transpose AP is equal to D, and since it is orthogonally diagonalizable, so P transpose is nothing but P inverse. So, D is equal to P inverse AP. So, we can write down A is equal to PD P inverse from here, and that means A is equal to PD P transpose. From here we can calculate the transpose. A transpose is equal to PD P transpose and its transpose, and further simplification will give me A transpose is equal to A. That means the matrix A is symmetric. Now, this completes the proof of this part. A implies C. So, if the matrix A is orthogonally diagonalizable, then the matrix is symmetric. But since we have given 3 statements and we have to prove the equivalence of all the 3, I have to prove C implies A also, but I leave this as an exercise for the viewer. Similarly, you have to show that B implies C and C implies B. This also I leave as an exercise for the viewer. Now, we will come to this statement that a symmetric matrix has real eigenvalues. This we have proved in one of my earlier lectures, and eigenvalues from different eigenspaces are orthogonal. So, this is the statement which I am going to prove now. So, to prove this, let us consider that there are 2 eigenvalues of the symmetric matrix A, which are lambda 1 and lambda 2. They are not equal, that is lambda 1 is not equal to lambda 2, and let us assume that V1 is an eigenvector corresponding to lambda 1 and V2 is an eigenvector corresponding to lambda 2. That means A times V1 is equal to lambda 1 V1 from this, and from here we can say A V2 is equal to lambda 2 V2. Now, we recall some of the definitions from inner product, that V1, dot V2 is equal to V1 multiplied by V2 transpose, and A times V1 dot V2 is equal to V1 times AT V2. So, these properties we use to establish result. So, we say we start with AV1 dot V2, and this is equal to V1 ATV2, which is from this property, and since the matrix is given to be symmetric, so A transpose is equal to A, so we can write down this is equal to V1 dot AV2. Now, I am using this in the first expression. A V1 dot V2 is lambda 2 V1 V2, and from here it is coming out to be lambda 2 V1 V2. So, from here we can rewrite that equation as lambda 1 minus lambda 2 multiplied by V1 dot V2 is equal to 0. Now, this means that either this is 0 or this product is 0, but since lambda 1 is not equal to lambda 2 which is being given to us, so V1 dot V2 is equal to 0, and that means V1 and V2 are orthogonal vectors, and that proves the result that if we have two distinct eigenvalues of a symmetric matrix, then the two vectors are orthogonal. Now, independent eigenvectors of eigenspace can be transformed to orthogonal vectors by Gram-Schmidt process of orthogonalization. Now, this means that we have a given matrix A, it will have some distinct eigenvalues, and those eigenvectors will be orthogonal, but there are some eigenvalues which are repeated, and suppose we can find independent eigenvectors corresponding to those repeated eigenvalues. The question is, can we also orthogonalize them? And yes, the answer is, and what we can do is we can perform Gram-Schmidt process of orthogonalization to transform the independent eigenvectors of the eigenspace. So, if we have repeated roots and has independent eigenvectors, then they can also be transformed to orthogonal vectors, and that way the whole set of eigenvectors for a given matrix A can be made orthogonal, and once we can have orthogonal eigenvectors, we can make them orthonormalize. We can perform the orthonormalization by dividing each vector by its magnitude. So, from the given set of independent eigenvectors of the matrix, we can get orthogonal eigenvectors, and then we can make them orthonormal also. And this gives us a method for diagonalization of symmetric matrix. So, the step 1 is find a basis for each eigenspace, apply Gram-Schmidt process to obtain orthonormal basis for each eigenspace, and from that we can form the matrix P, and finally we form the product P transpose AP, and this will be nothing but the diagonal matrix D consisting of eigenvalues in the diagonal. So, this procedure can be applied for diagonalization of symmetric matrices, and you may notice here that we do not have to calculate P inverse, simply P transpose is to be obtained to make the matrix diagonalized. So, we do not have to compute P inverse, simply P transpose is required for the process. So, let us illustrate this with an example. We have a matrix A, 2 by 2 matrix for simplicity. So, we have 2 1 and 1 2. We consider its characteristic equation, lambda I minus A is equal to 0 is determinant, determinant of lambda I minus A equal to 0 is to be obtained, and for this if you calculate this determinant, then this comes out to be lambda minus 3 into lambda minus 1 equal to 0, and that means lambda is equal to 1 and lambda is equal to 3 are two distinct eigenvectors of this matrix, these are two distinct eigenvalues of this matrix A. So, they are distinct eigenvalues. So, the vectors will be orthogonal. So, we start with lambda is equal to 1. So, we simplify the matrix equation A x is equal to lambda x. For lambda is equal to 1, this will be this system of equation minus 1 minus 1 minus 1 minus 1 x, and this simply means that 1 and minus 1 is an eigenvalue, is an eigenvector corresponding to lambda is equal to 1, because this vector will satisfy this system. So, we have obtained one eigenvector corresponding to this value. Similarly, we can obtain eigenvector corresponding to lambda is equal to 3. However, for however we need not only the orthogonal vectors, we need orthonormal vectors. So, we divide this by its magnitude. So, lambda is equal to so for lambda is equal to 1, we have this vector is a unit vector. For lambda is equal to 3, this is the system, and corresponding to this we have 1 1 as its eigen vector, which can be divided by its magnitude. So, corresponding to lambda is equal to 1, we have this eigenvector, and one can notice that this vector which we have obtained corresponding to lambda is equal to 1 and this for lambda is equal to 3, they are orthonormal. And once we have P, we can obtain P transpose by taking its transpose. So, we have this P transpose. Now, we have to check whether it is really being diagonalized or not. So, we form the product P transpose AP. So, this is my matrix P transpose. This is the given matrix A multiplied by P. So, first I compute this product, and this product comes out to be this multiplied by P. This is the matrix P which is given to me, and if you perform this computation, we perform this product, you will have D is equal to 1 3 0 0. So, this matrix is diagonalized. So, I have been given a symmetric matrix which is diagonalized with the help of P and P transpose. In fact, what we have done is we have done orthogonal diagonalization. Now, in this example, the question is, does there exist a symmetric matrix with eigenvalues minus 1, 3 and 7 with eigenvectors this, and if yes, then obtain the matrix A. That means, if we have eigenvalues given, if we have corresponding eigenvectors, can we find the matrix A? So, this is what we are going to do in this example. So, we have been given 3 distinct eigenvalues, and since eigenvalues are distinct, one can say then eigenvectors should be orthogonal, and by this I mean to say these are the 3 eigenvectors given to me, whether they are orthogonal or not. So, let us check whether this is perpendicular to this or not. So, I perform this product, comes out to be 0. I take the second product, this and this is also 0, and this is also 0. So, these 3 vectors are, these 3 are eigenvectors and they are orthogonal. So, that means there exists a matrix A which is having these 3 eigenvalues and corresponding eigenvectors, and the orthonormal eigenvectors corresponding to these given set of eigenvectors, they are 0, 1 by root 2 minus 1 by root 2 corresponding to first one, corresponding to second one it is 1 0 0 itself, and for the third we will have 0, 1 by root 2 and 1 by root 2. So, this is a set of orthonormal eigenvectors, and then I can form matrix P for some matrix A. So, this is first eigenvector, second eigenvector, third eigenvector, and P transpose is this. So, the matrix A will be equal to this P transpose D and P. So, A is equal to P transpose D and P. So, this is being given to me, this I have computed. So, from here I can compute A. This is possible because I could get this matrix P. So, if you perform this product, first this product which is coming out to be this, one can verify that this product is actually this. Then once we get this product multiplied by this, that means this, and computing this product, one can get this matrix. So, this is the matrix A which is symmetric, and we can obtain the symmetric matrix which is having eigenvalues which are specified and eigenvectors which are given, and from there we can find the matrix P and P transpose. So, this is a reverse problem. I have been given eigenvalues, I have been given eigenvectors, and I have to find the matrix. So, this is possible in this manner. In the next example, if I have the matrix A and I have to find A cube. See, in the beginning I said that with the diagonalization, the computational effort will be less while performing algebra on matrices. So, let us see how the effort will be simplified for this matrix A. I have to compute A cube. If I have to compute A cube without doing diagonalization, etc. So, what I have to do is I have to first perform A, I have to first multiply A into A, getting A square, then A square and A will be multiplying to get A cube. But it is not only the matter of A cube, it may be A raised to power 10, A raised to power 30. So, if I have to do this way for each and every product, things will really be complex. So, let me illustrate a procedure in which you can easily perform such type of computations by using diagonalization. So, I am illustrating this concept with the help of A cube. I will start with a symmetric matrix A, which is this matrix, which is given, this is applicable only for symmetric matrices. So, this is a symmetric matrix. So, if I have been given a symmetric matrix, then I can write down this symmetric matrix as D is equal to P transpose AP, that is D is similar to this matrix, D is diagonal matrix. So, what is D cube? D cube is this multiplied 3 times, and since matrix multiplication is associative, so one can rearrange these terms to have P transpose at one place, this P transpose at again they can be combined, and we know that P transpose is identity, this P transpose is also identity. So, what we have is P transpose A into A into A, and that gives me P transpose A cube P. So, for this given matrix A, I know its eigenvalues. So, I know what is D. It is a diagonal matrix consisting of eigenvalues, and D is a diagonal matrix. Computing D cube is very simple, because what we have to do is we have to simply cube the diagonal elements, rest of the elements are 0. So, D cube is known. So, from this expression I can write down A cube as P times D cube Pt. That means, if I multiplied here P and post by Pt, then P into Pt is identity and this P into Pt is also identity. So, what remains on this side is simply A cube. So, A cube is Pd cube Pt. So, calculating A cube simply means calculate the diagonal and then make this product, and you can in fact generalize this result, and you can say D raised to power n is P transpose A raised to power n P. That means, you can get any power of A, and this can be given as A raised to power n is equal to P D raised to power n Pt. So, you have to simply multiply by P and P transpose. This is post multiplication, this is pre multiplication, and you can get the product. So, I apply this to calculate A cube. So, A cube is P D cube Pt, and this D cube is this P, it is I have already computed like this in my earlier example, and the eigenvalues are -1, 3 and 7. So one can very easily compute 3, it is 1 minus 1 raised to power 3, 3 raised to power 3 and 7 raised to power 3, and this is the post multiplication, and these 3 matrices are to be multiplied to get A cube. So whatever be the value of n here, and maybe 3, 10, 20, whatever it may be, I have to get only this product, and that is how we get A cube. So in this example I have illustrated how you can make use of diagonalization process to get your algebra simplified. So today in my lecture I have given you method of diagonalization, and we have discussed orthogonal diagonalization also, and with the help of orthogonal diagonalization I have simplified the process of diagonalization in the sense that I do not have to now compute inverses. I simply work with transposes, and that is only for matrices which are symmetric. So for diagonalization of symmetric matrices is simple, and then once we can get the diagonalization, the algebra will be simpler. So this is all for today's lecture. Thank you.
Thank you.